So let's begin. We are now discussing buckling with infinite degrees of freedom, and those systems are generally known as beams, deformable bodies. So far we discussed buckling of single degree of freedom systems. So we had a rigid bar, and there is a compressive load. We discussed a 2 degree of freedom problem, that when there are two rigid bars connected to each other, or actually three in that case, connected to each other, there were a couple of springs, we had 2 degrees of freedom. And we saw that if we have 1 degree of freedom, we get one equation. If we have 2 degrees of freedom, we have two different equations for each degree of freedom. And if we have infinite degrees of freedom, we should have infinite equations, right? Then we also discussed imperfections, that if the system is perfect and if there is a system with imperfections, then you can calculate P critical for the imperfect system and then compare it with the P critical of a perfect system. If it's more, then it's insensitive, but if it's less, the P critical is less than the P critical of a perfect system, then the system becomes sensitive to imperfections, right? You cannot go to the same amount of load that you could have in a perfect system. So the imperfections could be of multiple types. The eccentricity of the load, which we discussed in the last class. There could be a problem in which the bar is initially tilted towards the right, and that could be an imperfection. So there are some things which we can discuss through homework problems. I can provide you some supplementary material on how to solve for imperfections. But today we will discuss more on beams. So how buckling generally happens in beams. So for that purpose, we will take a simply supported beam to begin with. So there is a simply supported beam with material constants EI in bending, and there is an applied load P, and then there is a distributed load small p. Okay, so as we discussed earlier during our first buckling session, that when you apply an actually compressive load on a beam, it will bend. It will not just compress. If the actually applied loads are too high, then you will see a bending in the beam along with the axial compression. And when that happens, we say that there is buckling present in the system. Okay, so let's see. Let's try to write a governing differential equation for a beam which is in simply supported condition. Okay, so can somebody tell me what will be the governing differential equation for a beam which is simply supported? E.
D squared. Man, forget this.
Let me help you.
Yeah.
EI. D squared.
U2.
U2
equal to minus B.
equals to minus
AP.
Okay. So so far we have studied that the governing differential equation for a beam in bending is this fourth order differential equation. Okay. So let's try to rederive this. Let's see what we get. We'll take an infinitesimal element, somewhat exaggerated infinitesimal element, and we have Euler-Bernoulli beam. So the plane sections remain plane. Plane sections remain perpendicular to the reference line. Right, so this is the horizontal axis, this is the normal to the plane. This is the horizontal axis, this is the normal to the plane. Okay, so we have a shear force here, that's V2. We have a shear force here, that's V2 plus dV2 over dx1. dx1. Then we have a moment here, which is m3, and here we have m3 plus dm3 dx1 dx1.
Mohit, should the V2 arrows be opposite? Shouldn't be up on the right.
Very good. Okay, and we have moment. This angle is the slope du2 over dx1, right? Slope in an Euler-Bernoulli beam. But this angle becomes du2 over dx1 plus second derivative of u2 with x1 times dx1. So Taylor series expansion on the angle, okay, because we have large deformation, or considerably large. And then we have an axial load, which is P1 or P, capital P, and on the other side the axial load is P plus dP over dx1 dx1. Okay, so this is the case where we have large axial loads. We are trying to study buckling of a beam under large axial loads. So N, or let's say P, is much higher than the V2. Okay, so our axial loads are much higher than the shear loads. And in Euler-Bernoulli beam, we have an assumption that our slope is much less than 1, right? So the angle is small. Okay. So now we see we have a free body diagram of an infinitesimal element in a beam which is under large axial compressive loads, and it's the mode of deformation is bending. Okay, so what we'll do now is equilibrium. Sum the forces in x direction, or I1, let's say I1 and I2, and then I have I3 coming out. So I will sum the forces in I1 and equate it to 0. Then I will sum the forces in I2. I will equate it to 0, and I will sum the forces, sum the moments about I3 and equate it to 0. These are my equilibrium equations, right? So when I have to find a component of a force in I1, I would have to take cosine of this angle and this angle, right, for the forces. And if I have to sum the forces in I2, I have to take the sine of those angles, sine components of the forces, which will give me projection about I2. So now let me write those equations. So sum of the forces about I1 is equal to 0. That's my equilibrium condition. So this becomes minus P cosine of du2 over dx1 plus P plus dP over dx1 dx1. So a component of P along I1, then component of this axial load along I1. So I need a cosine of du2 over dx1 plus second order derivative of u2 with x1 dx1, right? And then I have components of these shear forces along I1. So I will get v2 sine du2 over dx1 minus v2 plus dv2 over dx1, its component sine du2 over dx1 plus second order derivative of u2 with respect to x1 dx1, right?
Why was it not this complicated when we did it? Or like just
Yeah.
like what assumption now?
So this axial load
Yeah.
is an additional term here
Uh-huh.
that's causing this entire term to appear.
Okay, so we didn't have but we did have axial load before.
Yes, but what we say is if the axial load is applied at the centroid, the problems are decoupled, right?
Yeah.
The axial problem and the bending problem are decoupled. So in bending free body diagram, you do not see any axial loads because we decouple them first.
Okay.
But in this case, a large axial compressive load is causing bending. So we cannot decouple the two, even if it's applied at the centroid.
Okay, so the key thing is that now there's a large axial compressive load causing bending.
Yes.
Okay, thank you.
So that's why we have these components. And then we have the distributed load P dx1 will go to 0, right? So now we have some simplifications that the angle is small. So the second order derivative of the angles will be neglected. So we get cosine of du2 over dx1 is almost so this is like a small element of length dx1 and there is a distributed load x1 or p on it, small p.
You're assuming that
Mm-hmm.
small distribution between them is actually
True. Yeah. Okay. So
I mean, there's probably simplifications for it, but
yeah. So essentially, that component will be very small, that it will essentially go to 0. So yeah, let me say p I1 dx1. Okay, so component of p along I1 in that small element dx1. So I'm just simplifying that expression and writing it here. So it will essentially go to 0. And then we have sine of du2 over dx1 almost equal to du2 over dx1. So from the small angle approximations, I get these two equations to simplify my expressions.
So that's little p now?
Yes,
that's the distributed load.
That's the contribution of distributed load on this element along I1. Because this is now curved, it's not no longer along I1.
Okay.
So if it was just along I1, you would not see that component.
Yeah.
Right?
Okay.
So when we simplify, we get d over dx1 capital P minus v2 du2 over dx1 is equal to minus pi1, right? And this component will be almost equal to 0 because it's very small. Okay, so similarly, okay, now we said that our P2 or P capital P is much higher than V2, right? Because it's the condition under large axial loads. So this term is much smaller than P, right? Yes, go ahead.
In that equation, the second line v2 sine du2 over dx1. What's the sign for that equation?
So V2 is in this direction, right? So if you have to take its component of this angle, it will be a sine component, right?
Right. But this whole thing is one equation, right?
Yes, this entire thing is one equation, which is,
You didn't put any plus or minus.
oh, okay,
Okay, thank you.
sorry. Yeah, this entire equation is equilibrium about I1. Yeah, go ahead.
In the diagram, did you mean to have a du2 squared somewhere in there? Like, where does that come in?
So the angle here is du2 over dx1.
Okay.
When you apply Taylor series expansion, you will get a second order derivative here.
Okay, so that is squared.
Yeah.
So it wasn't squared.
Okay, sorry. So in the end, when you say that small p1 is equal to 0, you're saying that the distributed load is not actually existing?
So the distributed loads component in I1 is negligible.
Okay.
Yeah. Small p I1.
Okay.
Yeah. Because the angle which is there is very small. So okay, and now we have equilibrium in I2. So it will be again a big equation, minus v2 cosine of du2 over dx1 plus v2 plus dv2 over dx1 cosine of du2 over dx1 plus second order differential of u2 with respect to x1 dx1 minus p sine du2 over dx1 plus p plus dp over dx1 sine du2 over dx1 plus second order differential with respect to u2 dx1, right, plus small p component in I2 dx1 is equal to 0. So component of small p along I2 dx1 is equal to 0, right? Okay, so simplifying this equation, again applying the small angle assumptions, we get d over dx1 v2 plus p du2 over dx1 is equal to minus p. Okay, because the distributed loads are applied in I2, so their component in I2 will be almost equal to p, small angle assumptions, right? So this is one important equation. Okay, and now again we will use the equilibrium equation which is associated with moments. So summing the moments about I3, it would be a similar equation to the one which we have seen before in Euler-Bernoulli beam theory, right? Because there is no component of axial loads now, so it will become minus m3 plus m3 dm3 over dx1 plus v2 dx1 is equal to 0. So we will get dm3 over dx1 is equal to minus v2. So this equation we have seen before in Euler-Bernoulli beam theory, right? So we will combine the two equations, the two most important equations we've got now, and when we do that we get the fourth order differential equation,
But if we're using V2
So, so in this equation, the contribution.
in that, so for the moments, because now we're saying that they all have contributions the two in the two directions, so wouldn't we also have to take their components and then multiply by like dx 1 over 2 or wherever they're applied, or no, am I wrong?
So we do that even in Euler-Bernoulli beam theory, right? When we
Yeah.
do not have actual components, and we still get this equation,
Oh, okay.
isn't it?
Yeah,
You should check it out.
No, I'm sure you're right.
Yeah.
Thank you.
I think it includes that, but they cancel out.
Okay, so we're
Or-
just not including it because they cancel out.
Yeah.
Okay. Thank you.
Okay, so now the equation, using the two main equations that we developed, we will get that fourth order differential equation term plus a second order term which has the axial compressive load is equal to minus P. Go ahead.
I'm still not fully convinced how the distributed load cancels out.
So I'm actually running out of time. I would suggest
Okay.
look at it again in the Euler-Bernoulli beam theory chapter, and you'll realize that this is the equation. We are not changing anything in terms of the distributed load. What we are doing is taking the axial load and trying to find out how that affects the equation. Okay, so we can discuss this after class. So now let's compare the two equations. We had this governing differential equation before, where we did not have any axial compressive load or a coupling between the two, like bending and axial. And now that we have an equation where we have contribution of axial load, right? So you see a term which directly enters the equilibrium equation as opposed to boundary conditions, right? We use or generally put concentrated loads in boundary conditions, but if you have large axial loads, the concentrated load will enter the governing equations, right? So this is one of the main equations which we consider for analysis of buckling in beams. The axial load, which is concentrated, it enters the equilibrium equation rather than the boundary conditions. Okay. Can I erase this? These lecture videos are also available to you in Media Gallery on Canvas. So if you think you have missed out anything, you can go there, download the video.
Has the bending slide deck been put up yet? Because I have the buckling slide deck been put up because I haven't seen it yet.
Not yet, I think, yeah. Because I don't think there is any slide deck for buckling. So if it's not there, we will prepare it and put it on
Yeah,
that.
I haven't seen it.
I will put my notes,
Okay.
handwritten notes and supplementary material anyway. So
Okay.
you will have them
Thank
if
you.
you want to look at it again. Also for buckling, if you want to study in detail, I would recommend using a book which is Fundamental of Stability by Simitsis, George Simitsis. That would be a very interesting book, or which elaborates on buckling part rather than the textbook. Okay, so now let's take a problem. So we have a simply supported beam. Under axial loads. Okay, and there are no distributed loads. We are now trying to find what is the critical value. Go ahead. Yeah.
Sorry, is it simply supported because there's two rollers?
Yes, I actually wanted you to point out that here there is no point of having this P, but nobody did that. So it is simply supported beam, and there are two rollers because this P is applied at both ends, so this will keep the beam in equilibrium. It will not let the beam move in the axial direction. So essentially what simply supported does is prevent displacement and exactly, yeah. So okay. So now we will write a governing differential equations. EI, fourth order derivative of u2 with respect to x1. If this is my coordinate frame, and I'm assuming that EI is constant along the length. If the beam is homogeneous and EI is constant along the length, like it's not tapered or anything, then we can take the derivative inside. And then I have the term related to the axially compressive load, second order derivative with respect to x1 is equal to 0 because there is no distributed load now. Okay, so this equation which we derived can be reduced to a fourth order differential equation with 0 right hand side. Now we will look at our boundary conditions. So we have the displacement u2 at x1 is equal to 0 as 0. Then we have u2 of x is equal to x1 is equal to L 0 because there are simply supports here, so they won't allow displacement in the vertical direction. So these two boundary conditions at the ends, if the beam is of length L. Okay, and now we have the moment boundary conditions. So at both ends I have a moment boundary condition, right? So let's look at the governing equation and try to simplify it. We can rearrange some terms and write it as fourth order derivative of u2 with respect to x1 plus p over ei second order derivative with respect to x1 for u2 is equal to 0, which we can rewrite as fourth order derivative of u2 with respect to x1 plus k fourth order second order derivative of u2 with respect to x1.
Sorry. Does the load has to be symmetric? So has to be p or can be like p or and the other side p over 2?
If you have roller supports,
Well, I mean, in this particular case, yes. If you have roller, it will move, so nothing will
yeah.
happen. But if you have like a physical support,
For example, this,
yes.
then if you apply p over 2, the reaction is also p over 2 for equilibrium, right?
Yeah.
So it will always be same. So yeah, I just removed that fixed support, replaced it with a roller and a force in this diagram. So rearranged some terms in the governing differential equation. Then we said p over ei is k, just to simplify this equation. Now let me erase this. So we have seen that equation before. It's essentially a fourth order differential equation. So a general solution for the differential equation can be written as u2 of x1 is equal to a1 cosine or sine kx1 plus a2 cosine kx1 plus a3 x1 plus a4. So this is a general solution for the differential equation, and if we use the boundary conditions, solve for these constants, we will have a solution for the displacement. Okay, so when we substitute or when we apply boundary conditions, we get 4 equations in A1, A2, A3, A4. So we will get 4 algebraic equations when we apply the boundary conditions on this general solution. Then we will get 4 algebraic equations in A1, A2, A3, A4. Okay. Now either we have a trivial solution that my A1, A2, A3, A4 are all 0, right? That will satisfy this equation. Or the other solution is that determinant of this matrix goes to 0, right? If my determinant of this matrix goes to 0, then I have a non-trivial solution for A1, A2, A3, A4. So let's see what happens when determinant of the coefficient matrix is equated to 0. So we get sine KL equals to 0. And this equation has infinite solutions such that KL is equal to n pi, where n takes values from 1 to 3, 1 to so on, and these are all in positive integers. Okay, so when we subject the determinant of the coefficient matrix equal to 0 for the non-trivial solution, we get sine KL equals to 0, where KL is equal to n pi are the infinite solutions for this beam, and n can take values from 1 to 3 to so on up to infinity, and these are essentially the eigenvalues of the system, and if you take one of these values, you will get the eigenvectors, and you have infinite modes in which the buckling can happen. So for example, let's now if we have KL is equal to n pi, we can write P bar as n square pi square EI over L square, because K is equal to P over EI, right? So P bar becomes n square pi square EI over L square, and the critical load we define when n is equal to 1. So for the first mode, whatever value of P bar we calculate, or essentially p in our case, whatever value we calculate for p is going to be the p critical for the first mode. So p critical is pi square ei over L square. Okay. So I want to show what it means. For example, if you have the first mode in which n is equal to 1, so your beam has applied P force, the mode of deformation will be something like a sine curve. Okay. So displacement is such that it is u2 of x1 is equal to a1 sine pi x over L. Okay. In the second mode, when n is equal to 2, when you have applied P load, it will be something like this, but yeah. Okay, and then for n is equal to 3, it will be something like this. So you can say that, let's say my mode is the second mode, then the critical load which is required to buckle in this mode is going to be 2 square pi square ei over L square, means 4 pi square ei over L square, right? But think about this. If this beam is going to buckle, it's going to buckle in this mode first, right? As you go on increasing the axial compressive load, you will hit the value pi square ei over L square first, right? So the smallest value at which your beam buckles is going to be your P critical. That's why we chose the P critical as the value of P when n is equal to 1, because that's the smallest load. When you reach that load, the beam is under buckling, right? So let's look at a case where the beam is under a cantilever condition such that it is cantilevered at the left end and is free at the right end. So we have this same differential equation, the fourth order differential equation. So fourth order differential of u2 with x1 plus k squared d u2 over dx1 squared is equal to 0. And then we have the displacement at this end and the slope at the left end where x1 is 0 is equal to 0. Okay. So we have the slope and the deflection 0 at the left end. We have a free end at the right, so we have the moment at the right end 0. Go ahead.
Why is it k squared instead of k?
Okay, so let me see. K. Okay, so it's actually k squared, and in the previous problem also we will put k square in the differential equation, and we say k square is p over ei. So it's k squared. So k squared is p over ei. So we have moment 0 at the right end, and we have another equation which is the shear force equal to 0, right? But we need to find out what the shear force is, because we haven't actually applied load at the end, right? So let's draw the free body diagram of the right end. We have a beam like this, where we have a P force applied horizontally, and then this makes an angle here. This angle is du2 over dx1, and my shear force is like this. So if I apply equilibrium equation on the right end, the sine component of this load P is going to be acting in the direction of V2, right? So I need to add the sine component of P, the shear force, and then equate it to 0, because we haven't actually applied load, which is also causing bending in the beam. So our shear differential equation changes to ei third differential of u2 with respect to x1 plus p du2 over dx1. So sine of du2 over dx1 is approximately equal to du2 over dx1, small angle approximation. So this term becomes p times du2 over dx1 is equal to 0. So this is going to be the shear force boundary condition, and not this term equals to 0.
Probably doesn't matter, but shouldn't the V2 shear force be where the cut is made in the diagram?
V2 shear force will be?
In the where the cut is, like where you make the cut.
Oh yeah, I mean, yeah. So
change the equation, but just making sure.
it would not change the equation though, but it's just a matter of writing the signs. So yeah, you should follow the directions which Professor Rosini has discussed with you, because I have a different convention in my mind, and that always is an issue of writing the equilibrium equations. So follow the conventions which have been discussed in class and try to derive this equation. You should get the same equation. Okay, so now when we have these boundary conditions and we make use of the governing differential equation to write a general solution, so the general solution will be the same: a1 sine kx plus a2 cosine kx plus a3x plus a4. So using the general solution, which is u2 x1 is equal to a1 sine kx plus a2 cosine kx plus a3 x1 plus a4. So when we apply the boundary conditions on this general solution, we get 0, 1, 0, 1, k 0, 1, 1 minus k square sine KL minus k square cosine KL 0 0 0 0 k square 0.
Which is the fourth boundary condition over here?
Yeah, so this is the fourth boundary condition.
Okay. Oh, for the load. Okay.
Yeah.
Yeah, sorry.
So the shear force boundary condition is altered because of presence of the axial compressive load, and that you can derive from the equilibrium equation at the right end. So when you have the general solution, you apply the 4 boundary conditions, then you will get the determinant of this matrix is equal to 0. So the solution here is k raised to power 5 cosine KL is equal to 0, then cosine KL is equal to 0. Okay, so when you find the p value here, it will be 2m minus 1 over 2 whole squared pi square EI over L square, where m goes from 1 to so on up to infinity. And the P critical, of course, will be when m is equal to 1. So that will be pi square EI over 4 L square. So the P critical has changed in this case. It was pi square EI over L square in the last problem in which we had simply supported beam, and now it is pi square EI over 4L square. Okay, and the displacement will be u2 of x1 is equal to a2 cosine pi x over L over 2L minus 1. So this is going to be a displacement expression for this beam. So we discussed two cases, one of simply supported beam and one of cantilever beam. The key points are that the governing differential equation is changed because you have now the contribution of axially applied load, right? So the axial compressive load enters the governing differential equation for a beam in buckling. If it was a regular problem without buckling, without stability analysis, then you would just decouple the two equations, axial and bending, solve the problem. But in this case, you have buckling, so the axial forces are large, they enter the governing differential equation, and also the shear force boundary condition here is affected. In simply supported beam, we do not have any shear force boundary conditions, but in case of cantilever beams, we have shear force boundary condition at the right end. So this is affected because there is a concentrated load applied at the end, and that term would come in the shear force boundary condition, right? So we assume a general solution for the beam, we apply or subject that general solution to the boundary conditions, then we find a non-trivial solution for the system of equations. We get an algebraic set of equations, and for the non-trivial solution we have to equate the determinant to 0. Then we will get the infinite values that we need for the infinite mode shapes in this case, and the P critical will be the lowest one. The lowest value at the beam starts buckling. Okay, makes sense?